So we're going to spend the next couple of days reviewing factoring and solving equations with polynomials and quadratics. And we'll start with what I would go to as my first method of factoring is the greatest common factor type of factoring. And that is basically looking at all the values in the expression and seeing if there are anything in common in terms of factors in each term. So in this first example, I see I've got a 6 and a 27. A 3 goes into both of those, so I'm basically just going to take and factor out a 3 and then say 3 times what is 6a, that's 2a, and 3 times what is 27, that's 9. And then that is my factored term. In the second, you'll see we've got 3 terms now, but what we're again looking to do is see if there's any common factors or numbers or variables that go into every single item. So I see that in 3, 4, and 5, there is nothing in common in those numbers in terms of factors, but I have these x values, and there's an x squared in each of these. So I factor out an x squared, leaving me with 4x to the fourth minus 3x squared minus 5, and I'm done. And that's my factored term. Let's do a couple more. I see I have an m in common. That's the highest power that's in common in both. And in this next one, I have an x cubed in common in both. And now I need to find out what multiplied by mx cubed is equal to m squared x cubed. And that's just an m. In the second term, I notice I need an x to complete it. And now I'm all factored out. Another term, I've got a 20, a 15, and a 10. I know that there's a 5 in each of these, so I'll factor that out. I've got an a to the fourth, and an a squared. A squared is the greatest factor in all of them. Then I've got a d cubed, a d to the seventh, and d to the ninth. D cubed is going to get that done. And now I have to go back and say, what does 5a squared d cubed multiply by to get each of these terms? 5 times 4 is 20. A squared times a cubed is a to the fifth, and I don't need anything to multiply by the d cubed. Next, 5 times 3 is 15. A squared times a squared is a to the fourth, and d cubed times d to the fourth is equal to d to the seventh. Lastly, 2 times 5 is 10. A squared doesn't need anything, and d to the sixth times d cubed is d to the ninth, and that's done. In terms of factoring by grouping, typically you're going to have 4 terms. And what we do is we look to, as it says, group any terms that have common terms in them. So you'll see I have a couple options here. If I can see that the first one and then the second one have terms in common this way, I'll usually go with that first. So in this small portion here, I notice there's an x in common, which leaves me with y plus 2. And then in this term, I have a 3 in common, again leaving me with y plus 2. So that was like a small greatest common factoring of the two terms. Now there's also another greatest common factor in what remains, and that's the y plus 2. So if I factor out a y plus 2, then I have to say y plus 2 times what is x times y plus 2? Well, that's x. And then y plus 2 times what is 3 times y plus 2? And that's 3. And now my term is factored by grouping. So in this next example, I'm going to do the same type of grouping, the first two and the last two. I notice I have a 2 and an x squared in common in this first term, leaving me with a 3x minus a 2, and then a 5 in common, leaving me with a 3x and a minus 2. Once again, I see there's a GCF of 3x minus 2, and 3x minus 2 times 2x squared gets me the first term, and 3x squared minus 2 times 5 gets me the second term, and I'm done. Now, factoring in terms of an x squared plus bx plus c form, this is a quadratic. And the thing to note here is that I have a 1 in front of the x squared. So basically what we're looking to do, if you remember, is we're looking to find out what multiplies to c and adds or subtracts to b. So we're looking for two numbers that do that. So I'm looking at my c term here and my b term here. What multiplies to 12 and gets you 8? 6 and 2 are the first things that come to mind for me. So I'm going to put two binomials down. Start out with an x and an x because I have x times x is x squared. Then I'll say I need a 2 and a 6 to get an 8, but I need a positive 12 but a negative 8, so both those should be negative. If I FOIL that out, that's x squared minus 2x minus 6x plus 12, or x squared minus 8x plus 12, and this is my factoring. You can always FOIL them out and check to see if you're right. Next, find two things that multiply to negative 24 and add to positive 5. Well, I know I start out with the x and the x again. 8 and 3 are going to get that done for me. This time I need a negative, so I have to have a positive and a negative on these two terms. And then I need a positive 5. So my positive term should be bigger. That gets the 8, and the 3 gets the negative. Do some more. So now this is a little bit more difficult. I need to find two terms that multiply to 96 and add to 20. And obviously it helps to know your multiplication facts, so I've got x and x. And then 12 times 8 is 96. And again, I need a positive but a negative. And so I'm looking at that. I need either two negatives or two positives, and I'm going to go with both negatives. And that gets me my negative 20. Once again, two things that multiply to 144 and get me 25. Now, here's something that's a little bit more difficult. I know my multiplication facts, and I know that 12 and 12 is 144, but it's not getting me negative 25. Now, I know two things that do get me 25. That's 10 and 15, but that doesn't get me 120 or 144. So then what I'm going to do is I've guessed down a little bit. I went from 12 guess to a 10 guess. I'm going to try 9 and see if 9 goes into 144. And sure enough it does. I get 9 and 16. So then I've got x, 9, 16, both negative, problem done. It's helpful to put this little multiplication set over here and then just start checking numbers off, see if they work, and use your calculator. You'll always have one. So in terms of solving these types of problems, there's something called a zero product principle. And what we do is when we have an equation, we want to make sure that equation is set equal to 0. Once that equation is set equal to 0, it's fairly common to know that if I have two terms, a and b, and they multiply to equal 0, then either a equals 0 or b equals 0. And that works for any number of terms. 3 terms equal to 0 when multiplying, then one of the 3 must equal to 0. 4 terms, etc., etc. So I look at this problem, and while it's already in factored form, I want to solve it. Because it's set equal to 0, I have like an a term times a b term equaling 0. So either a equals 0, or 2x plus 1 equals 0, or b equals 0, 9, or x minus 9 is equal to 0. Solve these two. That's negative 1/2 is equal to x, and x equals 9. And we're going to use that zero product principle to solve pretty much any quadratic or higher power problem that we have. And the key is setting aside equal to 0. So you'll see in the first case, this is already set equal to 0, but it's not in a in a multiplied form. So what we have to do is we have to factor it to get two multiples, or two factors. I see that this is a GCF factoring, so I pull out a 3 and an x, leaving me with an x minus 4. That's equal to 0. Again, I have zero product principles, so either 3x equals 0, or x minus 4 equals 0. X in this case equals 0, or x equals 4. Now you'll notice in this case I can't use a zero product principle because first of all it's not factored, and secondly I don't have anything equal to 0. So what I'm going to do is keep my x squared term positive. That's always a big deal for me, is trying to factor with a positive x squared term, and then add the 12x to the other side. So let's do that. Not like terms, so I have x squared plus 12x is equal to 0. Now I can use a zero product principle after I factor, pull out an x plus 12 is equal to 0. Now I have two factors, so x equals 0, or x plus 12 equals 0. Thus x equals 0 and x equals negative 12. Again, you have to have a side equal to 0, and then you have to have factors in order to use the zero product principle. So in this case, again, I don't have anything set equal to 0. It's a quadratic because I have a squared term. I'm going to keep this 12a squared positive and bring everything else to the other side. In doing so, I get a 12a squared plus 3a minus 8a minus 2 equals 0. Now I've got four terms here. I could go ahead and do a grouping, which I'll do right now. I see I've got a 3 in common and an a in common, leaving me with a 4 and an a and a 1. Now in this case I have an 8 and a 2, and if I pull out a negative and a 2, then 4a times negative 2 is negative 8a, and plus 1 finishes that GCF. Once again, I notice these terms are in common. Pull out the 4a plus 1 and the 3a minus 2, and now I have a zero product principle going on. So I set 4a plus 1 equal to 0 and a 3a minus 2 equal to 0, leaving me with a equals negative 1/4 and a equals 2/3. So in this case, here's a quadratic. I can take and find out what multiplies to c adds to b. I know 9 and 5 is going to get me a 4 if the 9 is negative and the 5 is positive. There's my zero product principle. X plus 5 equals 0. X minus 9 equals 0. So x equals negative 5 and x equals 9. Now in this term not equal to 0, I'm going to have to do that. I notice in this case that I have a negative x squared. Personally, I never want to factor with a negative leading coefficient or a negative x squared term in this case. So I'm going to bring everything over to this side, giving me an x squared plus 4x minus 21 equals 0. Now I have a side set equal to 0. I can factor this. I know that 7 and 3 get me 4. 7 in this case being positive, the 3 in this case being negative. There's my zero product principle. X minus 3 equals 0. X plus 7 equals 0. So x equals 3 and x equals negative 7. In this case, I have my positive x squared, but no equal to 0, so I'm going to bring the 3x over to this side, giving me x squared minus 3x minus 28 is equal to 0. Two things that multiply to negative 28 get me negative 3 are a 7 and a 4, 7 being negative, 4 being positive. There's the zero product principle. X minus 7 equals 0. X plus 4 equals 0, so x equals 7, and x equals negative 4. Lastly, just something to note, these are all quadratics which graph as parabolas, like so. Now, in parabolas, if we were to set a y equal to 0, we're finding an x-intercept. All right. So once again, if I set this equal to 0, I could factor into this product here. Notice zero product principle, and I have x minus 3 equals 0, x minus 5 equals 0, and I get values of x equals 3 and x equals 5 when y equals 0. And what do you know? Those two values are x-intercepts. And that's going to be a big deal as we go through. So basically, the x-intercepts are solutions to quadratics when set equal to 0.